let's take a look at your CFU packet, chapter 2.1 problems. Today we're talking about percentiles and z-scores and looking at a relative frequency graph and predicting values from it. So the first example was just a nice review of percentiles. So if we take a look at number one here, it says old folks. Here is a stem plot of the percents of the residents age 65 and older in the 50 states. So notice how they give you a key to explain that what each of those values means. So it gives you kind of the percentage of residents that are 65 years or older. So in A it says find and interpret the percentile for Colorado, which is at 10.1% of its residents age 65 or older. So we want to find the percentile. Whoops, I hate it when it does that. Sorry about that. So I'm just going to hit undo here real quick. Get back to my pen. So we want to find what percentile 10.1 is. So here's where the 0.1 is located. So, or 10.1. And I count how many values are below it. 1, 2, 3, 4. Nice thing about the stem plot is that it's in order. We have 50 states here. So 4 out of 50 is 0.08, or you know that it's at the 8th percentile. So we could say 8th percentile. And so now it does ask you to not only find it, but interpret it. And this is, to me, the more important piece. Tells you that you understand what percentile means. So what we can say is something to the extent that 8% of states have a smaller percent of residents age 65 or older than Colorado. All right, so B does ask you to do the same thing for just another state. So here it says find and interpret the percentile for Rhode Island with 13.9% of its residents age 65% or older. So when I look at 13.9%, we're talking this value. So I got to count all of these values here, 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 and all of those. Well, one way of looking at it is if I count one, if I go backwards, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that means there's 10 states at or above, leaving 40 states below. So kind of a faster way of getting that 40 out of 50, which is 80%, or the 80th percentile. So again, what I want to do is, oh, I see here that E was left out in states, is just interpret it in the context of the problem. Same almost word for word, but I'm talking about Rhode Island here. So now I'm saying 80% of states have a smaller percent of residents aged 65 or older than Rhode Island. Which of these two states is more unusual? So is Colorado more unusual, or is Rhode Island more unusual? So the question is basically, which one's farther away from the center? So when I look at these, I would say Colorado is more unusual. The reason for it, okay, so I answered the first part, I do have to explain. Colorado is 42% away from the median, while Rhode Island is only 32%, I'm sorry, not 32%, 30% away from the median. So if we're thinking the median is like the average, or in our case, the middle, what we would expect to be right normal, Colorado is 42% away versus Rhode Island only being 30% away. Hence why Colorado is more unusual. All right, that takes care of number 1. Number 2, light it up. The graph below is a cumulative relative frequency graph showing the lifetime in hours of 200 lamps. So you can see here how we start at 500. These are the lifetimes all the way up to 1500, and this is the cumulative relative frequency, meaning what percent as we increase throughout from 0% all the way to 100%. So question A says, estimate the 60th percentile of the distribution. Show your method. So first thing you should do, and I'm just going to kind of note it here, find 60 on the y-axis. The reason why I'm saying that is this is where the 60th percentile. So you can think of these values as your percentiles, because it's cumulative, it's building up and it's counting more and more and more, and it's everything underneath it. So then what you want to then next do is read over to the graph and then read down to the x-axis, or on the x-axis. X-axis for your answer. So what we're saying here is at 68%, or the 60th percentile, you're going to go to the graph. Here's where it's located on the graph. We're going straight down on the x-axis to estimate where that point would be. Right? So again, lifetimes is in hours, so we would say it's about, it looks like it's about right in the center between 900 and 1100, so about 1,000 hours. So the 60th percentile for light bulbs is about 1,000 hours worth. So B just says, what is the percentile for a lamp that lasts 900 hours? So this one, we're just reading it in the opposite direction. We give you the lifetime, in this case 900, so we go up to the graph and then read straight across to get the percentile. So looking at how I drew that, here we're at 20, 40, pretty close to 40, not quite there. So what percentile? I would say about, looking at the way I have it drawn here, I'd probably say about the 37th percentile. Now, if you said 35%, probably would accept that. I would just make sure that it's probably somewhere between 30 and 39. It should be under 40, but it's definitely close. So it needs to be, I'd say, at least 35 up to, but not including 40. So again, this answer can vary because it's not at an exact point. All right, let's flip to the next page and and look at our last problem. All right, comparing batting averages. Okay. This is a great problem because this is where we can start to compare people from different eras, like in sports. It's always a good argument here, or a good discussion that sports fans like to have. So it says three landmarks of baseball achievements are Ty Cobb's batting average of .420 in 1911, Ted Williams' .406 in 1941, and George Brett's .390 in 1980. These batting averages cannot be compared directly because the distribution of Major League batting average has changed over the years. Sounds correct. The distributions are quite symmetric except for outliers such as Cobb, Williams, and Brett. While the mean batting average has been held roughly constant by rule changes in the balance between hitting and pitching, the standard deviations have dropped over time. Here are the facts. So in the 1910s, the mean was .266, standard deviation was .0371. 1940s, you can see it there, and 1970s, you can see it there. I'm just going to save a little time and not read it all. So it says, compute standardized batting averages for Cobb, Williams, and Brett to compare how far each stood above its peers. Okay? So, what we're basically, when it says standardize, that means z-score. So this is this formula you need to know, love, make your best friend. This formula you are going to use so much in this class. From this chapter on, it will come up many, many, many times. So a z-score is your score, x minus the mean, divided by the standard deviation. So we need to do it for all of them here. So we're going to start with Cobb. Cobb was in the 19 teens, so his z-score, okay? Well, he batted .420, that was his score, .420, minus .266, divided by his standard deviation, .0371. Again, I'm subtracting its mean and its standard deviation from up here. So now, again, when you enter this in the calculator, you have to do the top first, then divide. You can't, if you're going to type it all in at once, you better put this in parentheses. You should get a z-score of 4.15. So his score is 4.15 standard deviations above the mean. Wow. All right, continuing on, Williams. So his z-score, now his batting average was .406, so .406 minus, in his era the batting average was .267, but his standard deviation was a little bit smaller. So again, when we calculate out this z-score, we get 4.26. So he's even farther away relative to his peers. So then we take a look at George Brett. So his z-score, he only batted .390, but again, batting average was a little bit less for his era, and his standard deviation was even smaller. We calculate out that z-score. He is also 4 standard deviations above the mean, not quite as far as Williams and as Cobb's. So I just want to note and compare. So it says compare how far each stood above his peers. So I'm just going to write a sentence or two talking about what these numbers tell us. Well, the neat thing here is all 4 of them are at least 4 standard deviations above their peers. That is, as we'll continue to talk in this class, very impressive. So all 3 hitters were at least 4 standard deviations above their peers. So then, since I'm still comparing, I'm going to say Williams had the highest, followed by Cobb, and then finally Brett. So Williams had the highest Z-score, followed by Cobb, and then Brett. All right. Looks good. All right. Have a good day. See you tomorrow.